Hello. So in the previous video, we learned some examples and why we have to learn regression model, right? So here, let me like come back to more serious statistics. The simplest possible linear regression model looks like this. What you're doing here is you'd like to explain this y, which is the outcome, using information, your observations about x, right? X determines y, right? X affects y. And there are there are two parameters, beta 0 and beta 1. And in addition, we have error term, epsilon. So this make this makes a regression model. And we have their names, but the names are these days so much different in different contexts and different fields, different textbooks. But let me just tell you the most commonly used terms. Y is dependent variable. It's called the dependent variable because it depends on y. It depends on x. Y depends on x, right? And x is independent, as x is called the independent variable because it does not depend on anything else, right? So as opposed to dependent variable, x is called the independent variable. And beta 0 is called intercept or constant term, like it's more mathematical term. And beta 1 is the slope or the slope of like coefficient of x, right? So literally that's this is the mathematical term. And epsilon is the error term or the disturbance term, right? But in most cases, you like different textbooks use different names. Like say y is also called as the output variable, outcome variable, the response variable, right? And x is sometimes called as the explanatory variables, regressors. There are different names, but let's just call them y, x, beta, epsilon. So that's enough, right? Usually, if you say y variable, then people realize it's the left-hand side dependent variable. Left-hand side variable, y variable, is enough. And x, then most statisticians or related researchers understand that's the variable on the right-hand side. Okay, so don't worry too much about the terminology, and you can search on Wikipedia if you are curious what's the right terminology in your area. But in at least in economics, these are the standard. So as I said, we would like to predict y using x. That's what we are going to do. Okay, and that means like when you estimate beta 0 and beta 1, what you are doing is basically making a straight line, trend line on the scatter plot. That's exactly what the regression does, right? This is the result, right? So here we would like to make a line that go through the middle, in the middle of the observations on scatter plot. That's what we're going to do. And then beta 0 is the cost you have to pay even if you do not produce anything, like rent, electricity, right? Those things does not depend on your production. You have to pay that first, upfront, right? So this is exactly the intercept, meaning of the intercept in mathematics. And the slope, when output increases by 1 unit, how much beta 1 increases, how much the cost increases, captures the slope. Is the beta 1, that is the marginal cost, which is equivalent to the slope in mathematics, right? That this slope is beta 1. And when you draw the line, the straight line, and as you see, the observations are not exactly on the line. There are deviations. The observations actually is different from the trend line, and that difference is understood as the error, right? So epsilon is like, for example, if you observe a like cost here, but your estimated trend, estimated cost was here, and then your observation is lower than what you estimate, then the difference is just treated as an error. Something happened, like maybe in this month, productivity was exceptionally higher, so the cost was lower than expected. That's uh, that's the error, right? Error term captures the remainder. Okay. And so in summary, we are going to set our parameters. Our like estimation or statistical inference problem is like this. Our parameters of interest are beta 0 and beta 1. And our data, available data, are the pairs of x and y, right? They are paired. We observe two variables over n months. That's our data, right? So, like, because we set up what we would like to infer about, so then we need to just estimate them. We'll first estimate them, and then we will talk about hypothesis testing later, right? That's p-value, t-statistic, confidence interval, follow from the previous theories we learned in earlier chapters. And the default, the most common basic way to estimate those two parameters in the regression model is called the ordinary least squares estimation method. Like, I will explain what this estimation method is later. I will delay the details about this estimation to a later part of this slide because I first want you to show that I want you to show how we can apply the results first. Then you will see the idea of this estimation better. And also, you see the name is a little bit weird. Why do we call ordinary least squares? That's because there are a lot of variations of these estimation methods when you change the regression model. So, as I said, the regression model we discuss in this class, in this course, is really, really simple and basic, right? So, if you take 420, the next course, you are going to learn more variations of the regression model, and they have their own estimation method. They are called in different ways, like weighted least squares, generalized least squares, nonlinear least squares. There are different least squares estimation methods, but this ordinary least squares is the most basic method. So we call this ordinary. And simply, we call that OLS. We are going to use OLS estimator like this. Okay, then let me show you the data on Excel. Like, this is our data, the same data I showed you in the slide, 12-month output and cost. And by the way, let me move my base. So I'll show you how to do regression analysis on Excel, right? Go to Data tab, and then I believe you have this because we have used it in an earlier chapter, like in chapter 4. But in case you don't see data analysis button, you can go to like options here. Option, add-ins, and here the analysis toolpack. You have to install this. So in this case, like I already installed this, so it is inactive. But in case you did not install this, you will see analysis toolpack in the bottom list, inactive list, right? So then you add in you click the analysis toolpack and click go. Then it will be installed. But anyhow, I already installed it earlier. So you click this, and you have seen this earlier also. Like we used it when we learned covariance and correlation coefficient, and we are going to use regression, right? Find regression and click OK. And you have to choose Y range. So Y is the output, the left-hand side variable. Output is cost. Like, let me choose track cost. And X is output. We use output to explain cost. And the first row is label. And of course, the size of the X and Y must match, right? So there are 12 observations of cost. Then there must be 12 observations of output, right? Otherwise, error will pop up. And you can choose, options. I will try this line fit plot, and let's click OK. Then you see some table and line plot. So let's look at the scatter plot first. The plot first. So the blue dots are the observations that I showed you in the previous in the slide, and the red are the expected predicted cost, right? So red is predicted, blue is actual observation, and like you can just change style to here. You can change line. I will change it to solid line, and marker option none. Then you see what's going on, and change color. Line color is red. So in this way, you see the red line is the predicted line, predicted trend, and the blue is the observations. There are differences, okay? And then this compares predicted cost and the residual as a table, right? So like month from number 1 to like observation number 1 through observation number 12, we calculate, this table calculates predicted cost, and the residuals are also calculated, which means it's the difference from the actual cost, right? So your prediction is different from your actual cost. That is called residuals, okay? But the main table is these. These are the main table. Let me delete these tables because we are not going to use them for a while. Like I will delete unnecessary part. And so we are going to see what these mean. That's the goal of this chapter. We'd like to learn what these mean, and if they are too difficult to explain, I will skip them. So let's see. First, you know what this means. We have 12 observations. It's pretty easy to see what this means. And let me increase this. Okay, and you will see here coefficients, standard errors, t-stat, p-value, lower 95% confidence limit, upper 95% confidence limit. You can expect what they mean, right? So we have intercept and we have coefficient of output, right? So these are, coefficient of output and coefficient of intercept, these like that. So later I will explain what they mean in the end. Okay, let's go back to the slides. And I just explained how you can implement regression on Excel, okay? So, and you get this table. This is the main output table, and we are going to use this table as our sample. We are trying to understand this table. By the way, the numbers are exactly the same. I will post, see, those numbers are exactly the same as the slide. So I will also post the Excel file, so you can try it by yourself, see if you get the same numbers. You should get the same number, of course, right? And so what I'm going to do is I will first explain how we interpret those results first, and how we can utilize those results first. And then later, I will explain how those numbers are generated, how those numbers are generated on the behind the scenes. Okay, that's what we are going to do. And in particular, I will focus on these 3 aspects of the statistical analysis of the regression estimators. First, I will apply the standard statistical methods to those estimates, right? Confidence interval, hypothesis testing, right? You can expect already they are here, right? Standard error, you know. And then that is only about one parameter, like specifically, like namely the slope, the effect of output on cost. That's beta 1. And the second approach we can do is prediction. It is more about y, not beta itself, right? Y is of our interest, so we'd like to predict y. And finally, we can use the residuals. I showed you the difference. The residuals are also a useful information to see if our model is correct and how accurate your model is. So the residual is another important aspects of the model we can utilize. Okay, so let me explain one by one. They are like once you get these estimates, it's pretty easy to see how to use them. Okay, first, let's focus only on beta 1. I am a beta 0 and beta 1. I am only interested in the, like say, marginal cost or the fixed cost, right? Then you have to look at the estimators for beta 0 or beta 1. That's your interest. You just need to know beta 0 and beta 1. In this case, I'm not going to go to the details what we learned earlier chapters, but first, we know that there is a mathematical theorem that proves that the OLS estimators, those estimators are unbiased, right? So back here, these coefficients are point estimators. So 8.189 is the point estimator for the fixed cost. And 2.383 is the point estimator for the marginal cost, right? So this is beta 0's estimator. This is beta 1's estimator. So those two are point estimators, which we learned in chapter 9, I guess, like chapter 8. I'm not certain. But anyhow, and you may remember at that time, point estimators there are two criteria, two simple criteria to evaluate a point estimator. One is unbiasedness, and the other was the efficiency. And first, there, like mathematical theorem guarantees that they are unbiased, right? They may be wrong. That means these numbers may be wrong, but on average, there is no tendency to overestimate or underestimate. On average is correct, right? There is no overestimation or underestimation tendency. That's how we interpret this result, what you need to know first. And I told you the second criterion was efficiency, which means those estimators standard error is the smallest among regular estimators. And also there is another mathematical theorem that says they are efficient. The OLS estimators, you calculate, the Excel calculates for you is the most efficient ones. And additionally, the standard errors are already calculated for you. Standard errors of those estimators, the standard errors of the estimators are calculated. By the way, remember the standard error is different from standard deviation. Standard error is standard deviation divided by square root of n. Okay, so that's what it means here. So already these are the point estimators are on the first column, and they are unbiased and efficient. That's why we use OLS estimator. OLS estimator is very good. Okay. Okay, so we checked the first column, and the standard error is calculated in this way. Of course, you don't need to memorize the formula. Formula itself is not that important. So, by the way, excuse me. So, the model goes like this, and there is an error term epsilon. So, it has its own standard deviation. We call that the standard error of the regression. So, this is important. Its standard deviation is important. Standard deviation of epsilon determines the error of the model, right? So if the error is large, that means the data are very noisy. But if the epsilon standard deviation is small, that means your data is really nice and there is very little noise, little error, so your estimation will be easy and accurate. So how big the error is very important in your accuracy in your estimation problem. So we call the standard deviation in the error term as the standard error of the regression. That is here. Standard error means it's the standard error of the regression, which is standard deviation of the error term, right? So we cleared another number in the results table, okay? And this is calculated in this way. Of course, you don't need to memorize it, but remember, so epsilon is replaced by, epsilon is not observed, but you can calculate the epsilon after estimation, right? So residuals are calculated. You see the differences from the line. They are estimated errors, and we square that and sum them and divide by n minus 2. Here, the only thing you need to worry about is first, why we square epsilon without subtracting its mean. That's first thing. Second, why the denominator is n minus 2, not n or n minus 1. So first answer to the first question. Why epsilon is not subtracted by its mean, right? When you calculate standard deviation, we start from calculating the deviation and then square that and then calculate the average of the square deviations and then take square root. That's standard deviation. But we do not calculate deviations. That's because the mean of epsilon is always 0. An error term is on average 0. That is another, nature of an error term. It should be overall cancel out. So it is a pure error. So the mean is anyhow 0, so you don't need to subtract the mean. That's the answer to the first question. And the answer to the second question, why do we use n minus 2 instead of n minus 1 or n? When we learned sample formula for the variance or population variance formula, we learned the denominator could be n or n minus 1. It's related to that. The reason why we used n minus 1 is because when you calculate the variance, you have to consume one information when you calculate the mean, right? So when you calculate the mean, you are consuming one information. So when you calculate the variance as a second step, then actually your actual number of observation was n minus 1. That's why we have to use n minus 1 in calculating the variance. Now, when you calculate the standard error, before calculating the standard error of epsilon, you have to calculate beta 0 and beta 1 first, in the first step. So in the first step, you calculate beta 0 and beta 1, and then in the second step, you calculate the standard deviation of epsilon. So that means you have already consumed 2 information in the first step, right? So beta 0 and beta 1 information is subtracted in the denominator. Then only when you use n minus 2, then your estimator will be unbiased. It's like it's in line with the sample variance formula, right? To make your variance estimator unbiased, you have to subtract the consumed information first in the denominator. Okay, so I will continue our discussion in the next video. Thank you for watching. It will be just a summary of and reminder of what you learned in the earlier chapters. So it will be not that difficult. Okay, see you later. Bye.